Hello, welcome to this class, Smart Core Academy, giving you your favorite online courses. Before we dive in, subscribe below the video. Give me a thumb if you find it helpful in your life. So, in today's class, we are going to look at thermal expansion or thermal expansivity. If you look there are two terms. There is thermal and there is expansion. To break them down, thermal means to deal with heat. When we talk about expansion, deals with an increase in the object. Therefore, thermal expansion is an increase in the size of an object due to the application of heat. An increase in the size of an object due to the application of heat. We are going to look at three things under thermal expansion. First, we are going to look at linear expansion, and then we are going to look at area expansion, and finally, volume expansion. But in our class for today, we are going to look at linear expansion. Let's go. Linear expansion, that is number one. Linear expansion as a subtopic under thermal expansion is an increase in the length per unit length per degree rise in temperature. An increase in length per unit length per degree rise in temperature. Let's put it in mathematical expressions. Let's say mathematical expressions. We say mathematical expression of linear expansion. We say that it's an increase in length. Not to forget anything, linear expansion is represented with a Greek letter that is alpha. This one is called alpha, and that is the representation for linear expansion. Here we say that linear expansion is an increase in length per unit length per degree rise in temperature. Let's put it down. Linear expansion we say that it's an increase in length, that is change in length all over the original length. Let me first put it in words. Change in length all over the original length multiplied by the change in temperature. That is change in temperature. And that is all about linear expansion. We say that linear expansion is represented with the Greek letter that is alpha. We are going to put alpha to replace this one is equals to change in length. Change in length is the same as delta n all over the original length. The original length means the initial length, that is L1. L1 multiplied by change in temperature, which is delta T. We can also break this one down. Change in length can also be written as L2 minus L1, as well as change in temperature can also be written as T2 minus T1. Let's put it. We say alpha is equals to L2 minus L1. This is L2 minus L1, change in length, all over L1. Our L1 is what? Is the initial length multiplied by T2 minus T1. This is the same representation of this one. Let's find out the SI unit of linear expansion. We will get the SI unit of linear expansion from our formula here. Delta L all over L. Here, length is measured in meters. Let's say alpha is equals to, we represent them according to their SI units. This is represented with meter. Also, this length is also meter all over meter. Change in temperature, we know that the standard unit for temperature is Kelvin. We are going to put Kelvin. Here we cross this and this one. We are going to be left with 1 out of K. You can also write it as per Kelvin. And this is the SI unit of linear expansivity or linear expansion. we're going to look at examples on how we should deal with problems under linear expansion. This is an example 1 under linear expansivity. It says that a copper rod whose length at 30 degrees Celsius is 10.0 meters is heated to 50 degrees Celsius. Find its new length. You are also given linear expansivity or alpha as 0.000017 per Kelvin. So here we are going to list down the given parameters. Let's say solution given. Now we list down the given parameters. A copper rod whose length at 30 degrees Celsius is heated 10.0 meters. Now here we have temperature 1. Let's put it down. T1 as 30 degrees Celsius. We are going to convert this one to standard unit of temperature, that is Kelvin. Or by doing so, we are going to add it by 273, of which we are going to get what? If you add this one, we will get here 303 Kelvin. We go is 10.0 meters. That means we are also given what? Our L1 is what? A copper rod whose length at 30 degrees Celsius is 10.0 meters. Let's say our L1 has been equals to 10.0 meters. Is heated to 50 degrees Celsius. We have now got our temperature 2 also. Our temperature 2 has been equals to 50 degrees Celsius. 50 degrees Celsius, we also convert it to standard unit of temperature by adding your 273. Here we are going to say this one is 3, this one is 2 carry 1, that is 323 Kelvin. Find its new length. The new length is the what? The final length, that is L2 as b equals to question mark. But in also our question, we are given the linear expansivity or alpha. So alpha is also given as 0.000017 per Kelvin. Now here, these are the given parameters. We are asked to find L2, find its new length. So we are going to do our formula. Alpha is equals to change in length all over L1 change in what? Change in temperature. Let's now look around. We say that it is also the same as alpha as b equals to change in length is equal to L2 minus L1 all over L1 into T2 minus T1. So we are going to see, this is what we are looking for. We have L1, we have T2 and T1, and we also have linear expansivity. To make this one the subject, we cross multiply. This time is this one comes here, L2 minus L1 as being equals to. We also multiply this one because we need to make this one the subject. So this time is this, you will get L multiplied by L1 into T2 minus T1. Still, we have this one on our right hand side of the equation. We're going to take it to the other side of the equation, say that we are left with only L2. Well, by doing so, we are going to say L2 as being equals to alpha L1 into T2 minus T1. If you take this negative sign to the other side, it will be positive. Then plus L2. L1 I mean. So from there now, we are good to substitute our values. We're going to say L2 is equals to the value of alpha. Value of alpha is here, which is 0.0000 0.017 times L1. Our L1 is 10.0, 10.0 into T2 minus T1. T2 minus T1, it is this one minus this one, which is 3, 2, 3 minus 3, 0, 3. Then plus, you continue from here. We are bringing this one down because of space. Plus L1. Our L1 is 10.0. 10.0. Now let's continue from this side. Now we go through. L2 is equals to this one of linear expansivity and this one. So let's subtract this. We are going to subtract this from this one. Let's say L2 is equals to 0.00017 times 10.0 into bracket. We subtract this one from this one. If we subtract 323 minus 303. Therefore, let's see. We say that this is 32303. Here we'll have 0, so we'll have 2. So we are left with what? We are left with 20 inside here. 20. Then plus 10.0. Now we are going to multiply this times this one. Let's put it in our calculator. We say 0.00017 times 10.0. We are going to have L2 be equals to 0.00017 into 20 plus 10.0. This one is also going to be multiplied by 20. Say times 20. We multiply this times 20, we are going to get 0.0034 plus 10.0. Now we are going to add finally plus 10.0. Therefore, we are going to get L2 as being equals to 10.0034. That is our final answer for this problem, as L2 as being equals to 10.0034. And our unit for length is in meters. So let's look at one more example, and we'll see how to deal with problems under linear expansivity. This is our example 2 under linear expansivity. Says that 11.5 millimeters brass rod expands by 2.835 millimeters when heated from 25 degrees Celsius to 120 degrees Celsius. Find the linear expansivity of the brass rod. Now from here, we're going to say solution, and let's list down the given parameters. Say solution. Let's say given 11.5 brass rod. 11.5 brass rod expands by this one. That means here is our L1 and here is our L2. Let's list them down. Our L1 is B equals to 11.5 millimeters. We should convert this one to meters by dividing it by 1000, because this one here, if you are dividing it with by 1000, you say that 1 millimeter is equal to 1000 meters. Therefore, we're going to divide this one 11.5 divided by 1000. Let's put it 11.5 by 1000. We are going to get 0.01115 meters. L2 Our L2 is equals to 2.835 millimeters. You do the same thing, you divide it by 1000, say that you get it in meters. 2.835 by 1000, you're going to get, say, 2.835 by 2.835 by 1000. You will get 0.00285. 835, that is in meters. We also have heated from 25 degrees Celsius to 120 degrees Celsius. Here, this is our temperature 1, T1 has been equals to 25 degrees Celsius. We convert it to Kelvin by adding by 273. That is 298. We're going to get 298 Kelvin if we add this plus this. So our T2 is 120 degrees Celsius. You add it by 273 and you get, this one is 3, this one here is 9, and then this one is 3. That is Kelvin. Now these are the given parameters. Here we are going to recall the formula. Recall formula as alpha is B equals to, here the value of alpha is not given, it is what we are looking for. Alpha is given as change in length all over the original length times change in temperature. Here we say that change in length the same as L2 minus L1 all over L1 into T2 minus T1. That is the same thing if you break it down. So we say alpha is equals to, let's substitute the values. L2, our L2 here is what? Is 0.0115 minus L, this is our L1, I mean L2. L2 here is 0.00283 minus L1, our L1 is 0.0115 all over L1, our L1 is 0.0115. T2 minus T1, our T2 is 393 minus T1 is 298. Now we continue. We say alpha is equals to, we break this one down and this one down. We are going to subtract this one from this, and we are going to multiply this and this after we have subtracted inside the bracket. Now let's continue the upper one. We say 0.00283 minus 0.0115. Let's say, wait, 0.02835 minus 0.0115. Here we are going to get, this one is only 1 0, okay? We're going to get 0.01685 all over. We're going to deal with the downer one. Let's subtract this one, 398 minus 298. 393 I mean, 393 minus 298. Here we are going to get 95 in this bracket. Let's say 0.0115 into 95. Let's keep this one. Let's keep the numerator. Say alpha is equals to 0.01685. Then we open the bracket by multiplying this one times the bracket. Let's say 0.0115 times 95. We are going to get 1.0925. Here, this is when we are going to divide this one by this one, say that we get our final answer, that's linear expansivity. Let's say 0.01685685 divided by this one, which is 1.0925. So our final answer here is giving us 0.0154, and the rest you leave it in 4 decimal places, and our SI unit for linear expansivity is per Kelvin. So this is the end of this problem. After we were asked to find the linear expansivity, we have come to the end of this class, and that is linear expansion. See you in our next class, that is area expansivity. But please, before we dive ahead, give a subscription down below this video. Like if you find it helpful. Follow me for more. See you in our next class.